welcome. Is this the one?
It's for there.
Okay.
Yeah, it won't actually.
Okay. This is Paul Jackson. He is a fourth-year pharmacy student with 3 years of research, and his topic is on asthma.
Thank you. Hi there. So I've been working with Dr. Maarsingh for quite a couple years. And we've been performing a lot of research on specifically allergic asthma. Now, personally, I'm affected by asthma myself, and Dr. Maarsingh is quite the expert in the area, so we're quite a good match in a sense. So, looking at asthma and kind of looking at background, how many people exactly have asthma? So we can kind of see in the population, there's 334 million people in the globally that have asthma. So we see there's a large amount of people. Allergic asthma causes bronchoconstriction, inflammation in the lungs of those affected. Those mediators that are attributed to this bronchoconstriction are going to be those of histamine, tryptase, leukotrienes, and prostaglandins. So you have allergic asthma, you have early phases and late phases. So the early phase reaction would be more of a histamine kind of occurrence of bronchoconstriction. And a late phase reaction, which would have about 12 hours later, be that with like a prostaglandin or leukotriene. So looking at that, some of the features of actually an asthma attack and asthma itself is airway hyperresponsiveness. So people who are allergic to, would you say, chemicals or allergens or eggs and other allergens out there. And so they're sensitive in a sense. And so they have more of an increased reaction. You also have increased airway smooth muscle mass. So if you kind of think about it, your bronchioles, which are the tubes, as you can see here, with asthma, if you have more smooth muscle, more constriction can happen. So obviously by more muscle, you can have more constriction. Fibrosis is a process that happens over time. As more asthma attacks happen and more constriction happens, in a sense, you will have fibrotic processes that happen. And fibrosis of the lungs would kind of look like processes that harden up the airways and making it hard to breathe, in a sense. That's like COPD-like factors and cystic fibrosis and uncontrolled asthma. Also, mucus hypersecretion is known also with this, and inflammation. So we can kind of see down there what's going on here. We see that there's inflammation, and we see that there's constriction, and we see that there's actual mucus secretion. So that can cause constriction, and that can cause hardness for a person to actually exhale and actually get enough oxygen in their lungs to live. So what we looked at was guinea pig models, and we had a total of 8 guinea pigs, and we sensitized them to ovoalbumin, which is egg protein, egg white protein, and it was sensitized for a 4-week time to let the immune system kind of get regulated to attack it if it ever sees it again. Now, the guinea pigs lived in allergen-filtered cages, which is important because they're kind of sensitive right now, and they were kept in pairs. Once the guinea pigs reached sensitization, they were sacrificed to recover their lungs, which is what we use to examine our findings. So, as you see here, to recover lungs, we use euthanasia. We had their lungs delicately filled with agarose. It's kind of a thickening kind of agent you can think of, kind of like gel, if in a sense. And we use isoproterenol, which is going to cause dilation. We don't want collapsing of the lungs in a sense. We want them to be open. And you have to use a syringe, you trach the animal, you put it in there and you inflate the lungs, and they become a nice model. After that process, we have to make sure to ice the guinea pig, and we have to kind of solidify the agarose so it doesn't move, and so we can keep the lungs nice and solid, as you can see in this picture here after they've been removed. After that, we take scalpels and we cut lobe by lobe and actually core out the sample. And when we core it out, we're preparing it for the next step, as we see here, agarose and core preparation. The next step is going to be actually slicing the lung tissue. So it is loaded in this end of the machine, and we this part actually drives it, and this is the slicer. So we're able to get very fine 500 micrometer slices, and the outcomes are actually pretty interesting. We can see, because we can see the bronchioles, you can see the vasculature that's going on in the lungs, and it's a really nice model in a sense. We obviously wash them, so we cut them, we wash them, we go through like kind of a sterilization wash, we go through another isoproterenol wash to make sure they stay nice and dilated, and we keep them in the incubator for overnight. The next part is we look at the findings via microscope. This microscope is very nice in the sense it's a Nikon where it'll actually videotape what's going on with these cells. It's a little tricky setting it up, but it's really awesome to see what's going on. Going more onto that is, here's one interesting video. The first video, a couple. So methylcholine is an M3 agonist, uses GQ coupled reactions in the sense to increase intracellular calcium. So to explain that more, in your lungs you have smooth muscle cells, and these smooth muscle cells need calcium in order to have their contractions. So when the smooth muscle cell has a contraction, it's going to cause the bronchiole to shrink up. We can induce this using methylcholine, and we just actually in real life we use methylcholine to asthma challenge people to see if they have asthma too. So we're going to challenge the guinea pig. And this is a slice. So as you see, as the increase of methylcholine happens, which is measured in log, we can see that over time the airway starts to constrict. And to complete, it's just gone. And at that point, you're not breathing, and it's not good. Next step. You can kind of see here, as methylcholine, as we increase the molarity, you can see that as time goes on, the constriction furthers. So the next step, we look at arginase. So the whole scope of this project is to examine arginase inhibition. When we want to give this drug to asthmatics in a sense in the future, so we can prevent allergic reactions from happening in the early phase, to try to stop that beginning part of that bronchoconstriction. So people who are sensitive, they can have more of that allergen causing, let's say egg, than you would before. So it kind of gives you like a little barrier, a protective barrier in a sense. So we can see with this one right here, as we treat the cells with arginase, that there is a difference in the constriction. And the next page will show us the graph. So what effectively is happening is there's less smooth muscle constriction, and there's less calcium in the cell in a sense. How this is working is where we're working at right now. Is it histamine? Is it another receptor? And I'm going to go through why we believe it is histamine and why we have evidence of this. So, arginase inhibitor. Okay. It's another arginase inhibitor. The names of the arginase inhibitors in the future, they're going to be ABH and NOR-NOA. And you can see here with the arginase inhibitor, there's a difference. And when we compare the graphs, we can see here, this is going to be your control. So this is not treated. The asthma cells, the smooth muscle cells are not treated. And as we increase the amount of allergen we give to the guinea pig tissue, we notice that there is a decrease in airway openness. So we notice when we give ABH and NOR-NOA, the arginase inhibition will actually cause a 30-fold difference between how much allergen we can give and how much bronchoconstriction there is. So give, for example, if we have 10 micrograms per milliliter of egg protein, and you're allergic to egg protein, you will be at almost no lung capacity, no opening in a sense. And if you do give that same concentration, we can see there's a 30-fold difference in how big the airway is. And going more into it. So what's going on here? How do we figure this out in a sense? So we know nitric oxide plays a role in actually bronchoconstriction and bronchodilation. And we wanted to see if we gave L-name, which is a NOS inhibitor, what would happen. So when we gave this, we saw that there was a difference, actually. We saw when we gave L-name in combination with ABH, the ABH doesn't work as well. So we know there's nitric oxide in the process. But what's going on with the histamine and the mast cells? So we actually gave histamine with all of the combinations of the arginase inhibitor and the L-name, and we notice there is a direct connection to histamine causing the bronchoconstriction. So if we go back here, we notice there is a large difference. There's a large difference with the medicines. So we notice there's some role in histamine playing in this pathway. Going more into that. I think we're out of time. So quickly, the last method of how we tested it, I took the tissues, I put them into individual silation vials, I warmed them, I gave L-name first so we can coat it with the nitric oxide inhibitor if it was actually to be tested with that, and then gave ABH. Then we gave higher concentrations of albumin, which would cause allergic constriction, and then we went and we measured the histamine. We're currently under analysis from this, but we can conclude that by blocking arginase, we're presumably inhibiting histamine from being released by these mast cells, thus decreasing the bronchoconstriction. Here's the team. And I would take this time for questions.
Okay, so now it's time for the Q&A. So does anyone have any questions written down for me to read to him?
What's the time frame between beginning and end of this process and extracting and treating and
Yeah. Okay. So we would extract the extraction would take about one hour, and the putting in the refrigerator, we do everything very quickly, and we would put the cells, the tissue, in the incubator overnight. So it's about 24 hours, actually. 24 hours, 26 hours, this whole process would be finished. So we would start, let's say it's Monday, we'd start at 10, then we would finish around 2 o'clock on Tuesday. So it's relatively quick. And the tissue I forgot to mention, we use a buffer, a physiological buffer. So they're in a medium where they're almost at home in a sense. So they're able to continue to thrive, and we give oxygen, well, we give CO2, and we let the respiratory process happen. So they're not, the tissue's still very much alive. Dr. Petrocco.
How do you sensitize the animal?
Okay, so we actually use kind of an immunization-like process where we give them ova-albumin, which is the egg white protein, along with a specific chemical that causes the immune system to be agitated in a sense. So with the agitation by the immune system, it causes the IgE to be eventually formed against this actual protein in a sense, the egg protein. It takes some time, it takes 4 weeks, and there's IgG, IgM, IgE, also immunoglobulins.
Inhalation or?
Oh, it's injection. We're giving it via injection. And by that, it's kind of like a flu shot in a sense. A little bit different. Nick.
So I'm not real familiar with ABH, L-name, and
Sure.
and OHA. Can you elaborate? What I mean, they're arginase inhibitors, but what's their how are they working? You know?
That's what we're defining, actually, the mechanism, how these arginase inhibitors work.
And what
So
are
what's the theory? Yeah, so we have 2 arginase inhibitors. That arginase inhibitor is called ABH and NOA. Those are going to be inhibiting arginase, which is, do I have it? Make it. So this process is actually good. So we see here with, camera shot, the arginase, when we inhibit it, there is going to be less, we inhibit the arginase, we're going to see that there is a decrease and the histamine be released by the mast cells. It's kind of the theory what's going on here, in a sense. And nitric oxide also does play a role in here, because we see that by blocking nitric oxide, we're going to be decreasing nitric oxide. Thus, there's going to be, which also bronchodilates. L-name is going to be blocking that nitric oxide dilatory process. And kind of a sense is we're trying to figure out what's causing that histamine from stopping to be released from the mast cell, and less calcium in the smooth muscle cell to cause a constriction. It takes a little while to explain, but that's the
So
brief
is
cycle.
ABH like your standard?
ABH is an orphan drug. It is not out in market right now, and it's not any trials. Dr. Maarsingh, is there any? There's no trials currently in it, but it's, in a sense, where would it place in therapy? It would be like montelukast in a sense, like a leukotriene inhibitor, but the idea is, instead of late phase, because leukotriene inhibitors work in the late phase, we're working in the early phase. So if they are equal in a sense, it can be very interesting. If they're non-inferior, which one would be best to use? Would you want to stop the reaction from happening at all? Or would you want to stop the late phase from happening, but still have the early? So you want to stop the early phase. So they have a therapeutic advantage.
If you have a lot of money, I will put some money on it.
Yeah.
Yeah, I will pay good scientists to do some good studies. Because it also inhibits late phase reactions too.
Right.
But maybe you can explain a little bit the paradigm there, L-arginine, Arginase, and NOS. That will maybe help him also.
Sure,
with the
sure.
balance.
So.
Just walk to the other side.
Okay. What's going to be happening is L-arginine is going to be, in a sense, converted through NOS pathways. We have extrinsic and intrinsic NOS. So we notice with intrinsic NOS that there is a production of a kind of a nasty little guy, and he's a free radical that is also going to play a role in this situation as we expand the model. What's going to be happening here is when L-arginine goes through arginase, it's going to be turned into L-arthane and urea. And if we inhibit that pathway, we're going to be increasing nitric oxide production. And when L-arginine goes through the NOS pathway, the good NOS pathway, we're going to be seeing that L-citrulline happens in a sense. So kind of think about, there's two ways it can kind of turn. It can kind of go into one that causes a free radical. Is it peroxynitrate?
I mean, we just keep it simple. So you produce nitric oxide through NOS.
Right.
It's like when you have money, you have a budget, and one spending it all on one thing, you can spend it on something else. Get rid of the one person, now the person B can spend it. So that's like, so the arginase needs the money, and either arginase or NOS spends the money. But if it NOS spends it, you get beneficial effects.
Exactly, because we want to see the better and increase without the free radical. Any other questions?
So what is your hypothesis with relation to the histamine release? Because you talked about it a little bit.
Sure. So
In different settings.
when we give ABH, we're going to be decreasing the histamine that's released from the mast cell. And what we can generate that from was here. We see this is kind of the role of nitric oxide and bronchodilation. And we see here when the histamine is increased, you're going to have the bronchoconstriction. So we know directly, as we can look at the models before, the control model. Notice how it goes to like the control right here with histamine, in the sense that there is inhibition of it, and because it works immediately in a sense. And we're going through and testing this more and more, and we're going to show, and actually the next month, the effect of histamine and concentration-dependent bronchoconstriction.
How do you measure the levels of histamine in it, or is it mostly clinically through the bronchoconstriction that you're observing?
We use an ELISA test. So we, back to this picture, right? Actually, right here. we keep the cells in the vial. We are going to give them the drugs, and we're going to give them the allergen-causing agent, and which will cause histamine release. Now we take the supernatant, the actual liquid that is in there, and we're able to actually measure out how much histamine is in there. We also lyse the cells too to see what's the total amount of histamine, because lung slices can differ in size, but we account for that, and we lyse it and we see what's the total amount of histamine, and then we look at the ELISA in a sense.
All right, thank you very much. Remember to fill out your evaluations, and yeah, thank you.
All right.